Hey everybody, in the last two videos I showed you how we designed and then installed a breaker panel for this camper trailer, and in this video I'll show you how we wired it all up. Pretty satisfying. In case you're new here, my name is Dan and I love to DIY stuff. I went to college for electrical engineering and robotics and then joined a conservationship for 10 years where I worked as an engineer. And during that time I learned a lot of different hands-on skills. A lot of skills that are actually very handy for working on a project like this. And in a way, this old Spartan Manor trailer feels like my own little ship. I hope to give you a good idea of how we installed everything in here, including selecting and running the cabling, putting in electrical junction boxes and dimmer switches, outlets including GFCI outlets, some fans even, lights, as well as a DC converter to power the 12-volt systems in this trailer. So I hope this video is useful for you. I wanted to film this video from inside the trailer today, but as you can see, it's literally freezing. So I'll be giving you some explanations from the comfort of my office. Since we have the overall layout of the camper planned out, it's just a bit of thinking to figure out where we want outlets, lights, and switches. You can do that on paper, but we found it best to be in the trailer and mark out locations for these items with pieces of tape. We want to be able to test the lights and outlets on the circuits as we install them, so we need to power this breaker panel. We only have a regular extension cord to power the trailer for now, so we have to cheat a bit here to test the circuits. Let me explain. First, we buy a cheap extension cord splitter, cut off one end, and strip off the insulation. You can see that this cord only has 3 wires, hot, neutral, and ground. That means we can get 120 volts. In contrast, this circuit breaker panel has connections for 4 wires, 2 hot wires, a neutral, and a ground.
If we look at the panel before we put the breakers in, we can see that one hot will power these 2 rows of breakers, and the other hot will power these 2 rows of breakers. The one exception is this double breaker, which connects to both hots, and that gives it 240 volts.
When we connect our one hot wire from the extension cord, that only gets half the breaker's power. So we need to put a short piece of wire from this hot connection to the other. That means we won't be able to test this double breaker, but that's fine. So now we can plug this camper into an extension cord, just like a tool, and test our circuits. And since the extension cord itself is only good for 15 amps and plugged into a circuit on a 15 amp breaker for the house, we should limit how much we're testing at a time. Since we're just doing lights and outlets for now, this shouldn't really be an issue. And whenever you're working on the wiring, make sure to unplug these cords. We're extra cautious by turning off all the breakers as well. Now we need to get power from the breaker panel to the location of each light switch and outlet. And for that, we'll use electrical cables. This type of cable with a plastic or non-metallic casing is called Romex. Romex is actually a specific brand name, as you can see here, but it's pretty much the generic term now, just like Kleenex is for tissues. Here's an example of a cable encased in metal, just so you can see the difference. These are the most common sizes of cable used in houses, 14-2 and 12-2. The first number refers to the size of the copper wires inside, or the gauge of the wires. It's kind of weird, but the bigger the number, the smaller the wire. These sizes are from the American Wire Gauge, or AWG standard. The size of the wire determines how much electrical current it can handle. A 14 gauge cable can handle up to 15 amps of current, and the 12 gauge can handle up to 20. The second number here refers to how many insulated wires there are in the cable, and you can see here that there are 2. But there's actually a third uninsulated wire here, which is the ground wire. You can see here it says with ground. So each of these wires are black for line or hot, white for neutral, and bare for ground. You can see each of these wires is solid, and that's what they're called, solid wires. But you probably noticed other wires are made of bunches of thinner wires, and these are called stranded wires. These 2 cable sizes are perfect for us because most of our circuit breakers are 10 to 20 amps. Our water heater, though, does require a cable much larger because it draws 60 amps. One important thing to note here, never install a cable that has a lower current rating than the breaker it is connected to. So this is okay, but this is not. Neither is this, even if you think the last outlet won't draw much current. This is because the breaker won't be able to protect that lower rated cable, and it could get hot, melt, and potentially cause a fire. So just don't do it. Now that we know which cable to run for each circuit, we can route each and pull them through. And I really recommend wearing some thin gloves like these. The sheet metal is sharp, and I got so many cuts doing this without gloves. We usually start by putting the coil of wire at the breaker panel and start feeding one end through the frames of the shell. This usually takes a lot of back and forth. And preferably we pass cables through holes like these that have metal grommets. When there aren't any of those, we put in little rubber grommets. If you don't put a grommet, over time and because of vibrations, especially if you're on the road, these metal edges could eventually cut through the insulation and reach the wires inside. If you don't have the trailer grounded, you could get shocked. But ideally, it would just cause the breaker to trip, but you would have no idea where to look since these will be buried in the walls. So make sure to put in some grommets. The sharp metal also shreds the coating of the cable pretty easily, so grommets are a necessity. I found mine at McClendon's, not at the other big box hardware stores. In hindsight, it would have been cool to buy some of those brass colored grommets. We probably could have bought the same kind used to make reinforced holes in tarps and canvas. Sometimes there are no holes to pass cables through, so we had to make our own. I got one of these step drill bits, and wow, these are awesome. It is so much easier than working up in drill bit sizes. Plus, I don't have any regular drill bits that are large enough. So definitely get a set of these if you need to make holes. When you reach the location of an electrical box, it's always good to leave yourself a bit more cable than you think you might need. It's easier to have extra in the wall than it is to have it too short to reach the box and comfortably attached to your outlet or light switch. Back where we started at the breaker panel, make sure to cut the cable, leaving plenty to work with. You'll need quite a bit of length to route inside the breaker panel neatly. And don't forget to label it. It's very easy to lose track of which cable is which. If you have a circuit that has many items on it, like we do with our main lighting and non-kitchen outlet circuit, you may find it useful to run it like this. As you can see, we're pulling down loops of the wire to the location of each electrical box and keeping the wire intact and running it all in one go. This allows us to install one electrical box at a time while keeping the rest of the wire intact, so we can test it after each addition of a switch or outlet, just to make sure. Before doing anything here, make sure your panel is not plugged into the extension cord. Back at the breaker panel, we can connect these cables to their circuit breakers. On the bottom of the breaker box, you'll see lots of circles that look mostly cut out. Some you can see have a few options, so just punch out the size you need. And you can use a screwdriver, hammer, and sometimes pliers to push them out and twist them off. In each of these holes, we want to install a strain relief clamp. These come in different sizes depending on your cable. They protect the cable from the sharp metal edges of the box, and when tightened, prevent any tugging on the cable from affecting the connections to the breakers. I bought some that are supposed to just snap in, but wow, those were hard to do. I prefer this kind that has a little circular nut you have to tighten. Once you strip the insulation from the cable and a bit from the end of each wire, you can connect them. The black or hot wire is secured inside the breaker by a screw between two small square metal plates. The white or neutral wire is secured by a screw into one of these neutral bars. And the ground goes to the ground bar. I had to buy this ground bar separately and screw it into the panel earlier. It's a bit messy now, but I'll tidy this up later. The first cables we ran were to the roof vents and the AC unit. All of these already had wires coming out, so we used junction boxes to connect them. Here's a small metal junction box and the two strain relief clamps we screw in to either side. I prefer plastic to avoid steel to aluminum contact, but I couldn't find a plastic one with the strain reliefs, but they must exist. Then you simply thread the stripped cables into either end, join the wires with wire nuts, and you're done. Close it up by screwing on the cover plate. We're not going to test the AC unit just yet. The roof vents run on 12 volts DC, so we bought this 360 watt DC power supply. We ran a 14 gauge cable to supply it with AC power and put these forked crimp connectors on the end to screw into the terminal strip. Black to line or hot, white to neutral, and bare to the ground symbol. Then we connect a 12 gauge cable to the positive and negative sections of the terminal strip and route it to the fan. In case you're not familiar, DC stands for direct current, and it's a steady voltage, just like what you get out of a battery. Whereas AC is alternating current, and the voltage goes up and down very quickly. DC current doesn't travel through wires as well as AC, so I'm using the 12 gauge cable here to help it as much as possible, even though the fan is very low power at 10 watts. That means it's less than 1 amp of DC current. You can take a look at tables like this online to figure out how big your cables need to be for DC powered devices, depending on how long the cable is. For the purposes of this video, it's enough to say that this 12 gauge cable works for these fans. After using another junction box to connect the cable to the fan wires, we're ready to test. Plug in the camper and flip the breaker for the DC converter. Very satisfying. Now before we do any more wiring, let's unplug the camper again. You can do this before running the cables, but for us, the next step was to place these electrical boxes which house the light switches and outlets. We chose plastic ones because they won't react with aluminum like steel boxes would, and they also have these handy tabs we can use to rivet them to the framing. We use pop rivets for that and put 2 or 3 in. And with these boxes, you can find them in what's called single gang and double gang to fit 1 or 2 switches or outlets inside. There are also shallow versions if you don't have much space, but it's a lot trickier to fit all the wiring in here. We put one of those up here where we'll have a shelf of some kind in case we want power up there. These boxes have built-in strain relief for the cables. You can see how that tab lets the wire pass as you push it in, but then won't let it pull out. So if you do need to pull a cable out, you'll have to use a screwdriver to pull back the tab. From the electrical boxes that will have light switches, you can now run the cables to where your lights will be. We were considering embedding LED strips into the ceiling for lighting, but then couldn't find a regular wall-mounted switch that was reviewed as being reliable and matched the simple aesthetic we want. We also didn't want to have a remote control for the LED light strip kicking around and getting lost either. So we decided to go with these standard downlights in the 8-inch and 6-inch sizes. These are nice and thin and should clip easily into the ceiling. Once we have one, that is. The only annoying thing is they have these large boxes for each one that you need to find a place to mount. But on the side here is a little switch that allows you to select the color temperature of the light, from daylight quality to warmer tones headed towards orange.
I personally like it at 3000K.
Inside the boxes, you'll see room to make a connection to the incoming cable, already with some connectors on there, and this DC power supply for the light. The box has punch outs, and you may want to put 1 or 2 strain relief clamps depending on your circuit, like if you're connecting to another light nearby. Then there's the little DC power cord with a keyed connector and a screw down fitting to secure the cables together. We simply riveted these boxes to the frames near each light. As a quick note, we also have these cool dimmable sconces for the living room, and these dimmable reading lights for both sides of the bed, but we'll install these another day. The only lights we don't have yet are the under cabinet lights, since the cabinets aren't yet in. We are putting all the lights in here on dimmers except for the one bathroom light. These are the types of dimmers we bought, and they were cheaper in these 3 packs. Dimmers are not as straightforward to wire as a regular light switch, and tend to have short wires coming out of the back rather than metal terminals with screws.
Start off by attaching the black wire from the breaker panel to the black wire of the dimmer.
Connect the neutral wire from the breaker panel to the neutral wire from the light bulb. Connect the hot wire from the light bulb to the red wire of the dimmer. In our situation, we can cap off this red and white stripe wire.
And finally, twist together the ground wires and put on a wire nut.
And now, secure the dimmer into the electrical box. And let's test it. Plug in the extension cord, turn on the circuit breaker.
Turn on?
Yep.
Plenty bright.
I think so. And test the dimming by moving that slider up and down. If the lowest setting makes the light go off or it's still too bright, there's a little slider here to adjust that. We move it until the light just turns on. We put in quite a few lights because with dimmers controlling them all, we weren't worried about it being too bright. For the bathroom light, we thought a dimmer was too much, so we got this double switched unit that fits in a single gang electrical box. One switch is for the light, and the other is for the fan. This is the standard 15 amp outlet, and you can get them with different shaped USB chargers built in as well. Outlets are simple to connect up. The back will say which terminals are hot and connect to the black wire, and which terminals are neutral and connect to the white wire. With screw terminals like these, I bend a clockwise hook into the wire so that when I tighten the screw, it tightens the hook. If you're connecting it to a 14 gauge wire, they also have little holes in the back that you can simply push the wires into. Here in the back is a little guide that shows you how much insulation you need to strip off. In either case, the green screw here means ground, so attach the bare copper wire here. If your circuit continues to another electrical box, you can simply connect those wires to the second set of terminals on the back of the outlet. We're planning on putting a convection/microwave oven combo under the counter here, and that requires a 20 amp supply. A standard outlet can only go up to 15 amps, so we had to buy this 20 amp outlet, which you can see has an extra feature on the neutral leg. This connects up just like a regular outlet. I'm sure you've seen these outlets with the test and reset buttons in your kitchen and bathrooms. These are ground fault circuit interrupter outlets, or GFCI for short. And sometimes just GFI for shorter, but they're the same thing. These are designed to protect you from getting shocked and are required for outlets near sources of water, like sinks. So we have one of these on either side of the kitchen. And what's great is that it can also protect outlets that are connected to its load terminals. This means that while our kitchen has 3 outlets on one side, 2 can be standard outlets that gain the safety features of the GFI outlet. That's very handy because regular outlets cost around $3 and a GFI outlet runs around $20. Installation is very similar to a regular outlet, but you have to pay more attention to the labels on the back. The hot and neutral wires from the breaker panel connect to these terminals, while any other outlets you want protected are wired to the load terminals. Attach the ground wire, and that's it. To test it, plug in the trailer, close or turn on the breaker for the circuit, test your plug-in power tool of choice, and see that it runs. Press the test button, see that the tool no longer runs, press the reset button, and see that the tool once again runs. You can repeat this test for any other outlets connected to this GFI outlet. There was an outdoor outlet near the front door that was in bad shape, so we had to replace that. That involved a bit of satisfying metalwork and riveting. We found this electrical box with a nice flange around the edge to help make a good watertight seal. We slid it into position, then turned these screws, which moved these little wings to secure it to the shell. Then we wired it up like a normal outlet and secured the weather-resistant cover on it. For the kitchen fan, we found this one that looks like a giant computer fan. And we also found this 3-speed switch for it. The wiring is similar to that for the light dimmers. And here you can see it running at different speeds. For the bathroom fan, we didn't have much room and didn't want to make another hole in the shell, so found another computer-like fan. So this one we simply wired into the second switch for the bathroom where we wired the light earlier.
And here's the difference between a 20 and a 60 amp cable. This 6-gauge cable required bigger holes, bigger grommets, and was harder to pull through the frames. Brought it to the bathroom wall where the heater will be installed.
Make sure to cap those wires.
And left plenty of extra length. And then it needed a bigger strain relief clamp before being connected to the 60 amp breaker in the panel.
As always, make sure your panel is unplugged anytime you're working on it. With all the cables run, it's time to finish up the wiring in the breaker panel. Again, make sure your cables are labeled. We put in this piece of wood behind it to secure the cables in an orderly way and labeled them there as well.
From there, figure out where each cable is going to be held in a clamp and strip off the insulation down to that point. Then tighten up the clamp. Then figure out how long each wire needs to be to reach its breaker or terminal. Cut its length, strip it back, and screw it in. I tried to keep it neat by running wires in groups and making 90-degree bends in the wires.
Pretty satisfying.
You've seen this bathroom wall throughout the video, but actually I haven't shown how we built it, so we'll go over that briefly here. As you can see, it's a pretty standard 2x4 stud wall, which is going to house the instant hot water heater, as well as the switches for the light and the fan of the bathroom, which you already saw installed. It's also going to house the medicine cabinet.
With this, we want to take into consideration the thickness of the wall, because we want the wall to be flush with this edge of the window.
To make sure that this wall is perpendicular to the floor, my neighbor Scott suggested that we use a piece of plywood to use as a big right angle. To secure this wall, we sandwich pieces of the framing between 2 pieces of wood secured with a couple screws. We did that in 3 spots. We also secured the wall with 2 bolts from below using blocks of wood as washers, and this worked great. Overall, this part of the project cost about $1,400 to complete. About half of that was for the cabling and all the electrical boxes, and the other half was for the light switches, the outlets, the fans, and the DC power converter. In total, my mom and I spent about 50 hours installing all of this.
The next big step in the project is to do the plumbing. And we have the sinks roughed in here so we can try and figure out where the drain lines go. And then after that, we'll do the supply lines. So if you like this kind of stuff, hope to see you next time. If you're wondering how we designed and installed the breaker panel for this trailer, watch this video here. Hey, Og.
Hey, 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 hey.
Here, get that. Get it.
Stop, man.